I've also put up the information for the next lab. For those of you that might not have it, lab number 9, I posted set number 10. And although I didn't put these things up, I've already looked ahead till the end of the semester for a lot of areas like the homeworks and things of that sort. I think it's going to come out okay. I can say that. It sounds easy, but I still have to get the final project out there, and I'm still debating that. I'm looking at some new technologies for that might extend something from what I've done in the past, and I'm usually crazy like that, but I'll get over it soon. Either I'm going to do it or I'm not going to do it. Just like this Friday is the 15th, and I've got twin sons. That's the day they were born, but I also have something that rises pretty big on the 15th for most of us. Does anybody know what I'm talking about? What's big about April 15th? None of you are thinking about the government too much then, are you? Taxes are due. My taxes aren't done yet. But my wife tells me, and maybe I hope this is true, that because it's falling on Friday this year, they're giving us till Monday. Yeah. So I've got the tax software installed on my computer, and I started to import last year's return, but those of you that don't pay taxes or much in the way of taxes, you do it early, but those of us that pay taxes, there's no incentive to do it early if you have to pay money, so.
Just claim 6 dependents and get on here.
Well, I'm not going to get into a debate on politics because there was politics in the news last week, too. So what I hope to go through in the beginning today is at least clarify some of the things that I kind of forced upon you with the homework, but actually what I had you do in the homework, I think you're going to be able to say in retrospect was really a lot of what the first steps in the Z-transform boil down to, and that is just simply making correspondences and plugging things in. You guys ready to listen? So we've had the time domain and the frequency domain, and now we're going to move formally into the Z domain. I'm glad you came back. I saw you walking out when I came down the stairs, and I thought, that's how he does it. He walks out of the building. It's easy, right? If you don't want to come to class, I'm not picking on you. Anybody could do that. I could just walk out of here and go home and say I'm not going to teach class, but makes you think back to junior high and high school, though, when people were guarding the doors, and if you walked out, you might have gotten in trouble. The Z-transform is, like I was saying last week, it hides more of the details. Instead of having, like we did for the frequency response, the e to the minus j omega k, we just have z to the minus k when we compute the Z-transform. And what's hidden is the fact that z is, as I was saying last week, z is a complex number. So that buries a lot of the details in that. And we have the representation then when we go from x to x of z. That's supposed to be a script z, and I'm not very good at my cursive, but it's transforming from one domain to the other. I said earlier that getting to the frequency response was like taking the Fourier transform or the impulse response. The book doesn't say that until much later, beyond where we're going to stop. But that's really what we were doing. The Z-transform, it's safer really just because of the fact that we're hiding the details inside Z. So when we go backwards, we have the inverse Z-transform. And formally, the inverse Z-transform involves what's called the contour integral, which is something well beyond what you study in electrical engineering, unless you were to take an elective in complex variable theory from the math department. But the way we do the inverse Z-transform is by a lookup procedure. You just look at what are the candidates, and then we can plug in. And what we're going to be doing in the next chapter to do inverse Z transforms, the big thing there will be partial fraction expansions and a small lookup table. Remember, I asked you that before, who had been doing partial fraction expansions, and most everybody seemed pretty much familiar with that idea. So formally, when we do a Z transform, we go from the time domain or the end domain or sequence domain, so you can all think of them as being the same. And the time domain is the physical world that we live in. The Z domain or the frequency domain, like we were doing in the last chapter, are just ways that we have of viewing things. So the Z domain is an abstraction, but it's useful for doing analysis. So when we take and go to the Z domain, we generally think of having this relationship with a double-sided arrow saying we Z transform back and forth, forward and inverse transform. So formally, as an example, x of n would be the sequence domain, and then this x of z, which is defined as this, is the Z domain. When we're talking about pairs, transform pairs, this is what's going to be in our little table of Z transforms that will be useful in the next chapter. In particular, we have a relationship with the double-sided arrow, so we have in the time domain side an x of n, and then the Z domain side an x of z. So as an example of a first transform pair, suppose we have x of n is equaling delta of n minus n naught, just a sequence that has one value in it. It has an n naught, it has a 1 at n naught and has 0 everywhere else. So what does that Z transform look like? You plug it into the definition, and this is what we have on inside the sum. As the sum runs from 0 to n, or in actuality, what we're going to be doing here a couple pages from now, we're going to be saying with our Z transform, we're just going to generalize entirely, and let's scan over the entire axis from minus to plus infinity. And we're looking for where does that delta function hit. It hits when k is equal to n naught. So the only functional value that's going to come out of that double-sided sum is when k is equal to n naught, and that returns us out z to the minus n naught. So this would be our very first Z transform pair, just telling us that a delta sequence located at n naught becomes in the Z domain a z to the minus n naught. And this was what you used to do the homework, right? The examples on the next page pretty much just let you see by inspection, but this is formally this is our very first Z transform pair. So applying that to the signal down here, this example on the top of the page, which is like what you did in problem number 5, you just made those correspondences and used that transform pair to get the answer, right? And then if you wanted to go backwards, so we had the forward direction, again, that's my cursive Z, and then the backwards direction, generally put a -1 on it, goes back to the time domain. So the double-sided arrows are always going to mean you can go forwards and backwards just by inspection. So z to the minus n naught becomes delta of n minus n naught. And if I was to throw k times delta of n minus n naught in here, linearity just says that k just rides along as a scale factor. So that's another one of the properties we're going to look at of the Z transform. So those first set of examples are really, really trivial, and that's mostly what the homework focused on. A little bit more, though, was what problem number 6 had thrown inside of it, and I gave you some hints on that on Friday night, and hopefully those were helpful, but we're going to look at that, move into that part of it right now and some other properties. So initially we want to be able to do linear systems analysis with the Z transform. And one of the biggest things that we're going to be heading for is that, and I'm going to write this down, this is going to show up in a couple of pages from now. If y of z is x of n convolved, or y of n is x of n convolved with h of n, we're going to be able to establish that y of z is x of z times h of z. So we're going to get a result known as the convolution theorem for Z transforms. So we can do away with convolution if we want to work in the Z domain. Some of you are taking differential equations right now, right? I remember some people said they were taking it or have taken it. How many of you are taking diffie-q? Just one. You've taken it. Okay. So those of you that have taken it have seen the Laplace transform, right? The Laplace transform and the Z transform share a lot of things in common. Those of you that haven't taken it, you will see the Laplace transform when you take differential equations, or at least I think you ought to. If not, you're going to be using it in circuits and systems, for sure, absolutely. Laplace, absolutely. Laplace transforms are for continuous time signals, as Z transforms are for discrete time signals. But this thing that I wrote in red we'll spend some more time on, and this is going to be something we're going to be using for the rest of the semester. We're going to rely heavily on this convolution theorem. I know the convolution tables that we dealt with weren't all that difficult once you got the hang of the table, but they're still tedious. The Z transform techniques allow us to totally work in the Z domain, and then we can avoid the tedium of the convolution sum, if we so choose. I mean, we have that as an option. So we want to build ourselves up to the point where we can see that in the Z domain, y of z would be x of z times h of z. And homework problem number 6 had a little tiny taste of that in an abstracted way. You didn't have to look at it that way if you didn't want to, but it actually had a tiny taste of that. So to start with, what's the Z transform of h of n? We've already basically looked at that, but formally we can go back to the way we developed this for the frequency response. So to make it more formal, we can say, suppose we put into our system a z to the n from minus infinity to plus infinity. Remember when we did the frequency response, we did e to the j omega n, same sort of a setup, but now we're just going to put in an arbitrary z to the n. By the way, you can rearrange this to make it look like the z in this case, or back in the last chapter, the z was just e to the j omega. So it's a little rearrangement of the algebra. But plug in the z to the n, plug it inside the convolution sum. So in place of this x of n minus k, it's the z to the n minus k. And then bring everything outside that's not a function of the sum index, and that's going to be the z to the n that we stuffed in to begin with. And then we have left something in parentheses, just like we did in chapter 6. And that something left in parentheses is exactly the Z transform of the impulse response, which is what I have boxed down here. And this, for a linear time invariant system, has got the very special name of system function. The frequency response was when we had Z equal e to the j omega, but when we have Z in general as a complex variable, then we get the system function. Maybe it doesn't seem all that exciting right now, but we're going to be using that, and that definitely factors into that convolution theorem that I was giving you a precursor to up here. there it is right there. That's the system function. So now we actually have had three quantities all related to each other. We have the impulse response, the frequency response, and then the system function. So for the case of the input being this z to the n in the time domain, the convolution drops out of the picture and we instead have the system function times z to the n. Whereas in the last chapter we had h of n convolving with e to the j omega n. That, if you remember, was e to the j omega times e to the j omega n. And I'm getting lazy. I'm not putting the hats on top of everything. Because that's one thing I don't like about this book. The other books I teach out of don't use that silly hat. It gets to be annoying after a while to draw that thing in. Okay, well, what is the system function? Well, for the case of an FIR system like we've been dealing with, the system function is just a polynomial. And you can see that if we plug in an M-tap or M plus 1 tap FIR filter, h of z is just this polynomial in those filter coefficients. And it has m roots then, because it has m plus 1 coefficients, b0 through bm. It's got m roots to the polynomial. We can factor that. And that was part of that problem number 6, where I had instructed you to use the roots function. And you'll get to use that a whole lot more. In actuality, if we factor h of z into positive powers of z, which is what I'm doing right down here, we get a result that's going to be leading to the more general result that we'll see in the next chapter, and that is when we have it in positive powers of z, we can always clearly identify where the so-called zeros are and where the poles are. We'll be spending more time talking about that later in this chapter, and then in the next chapter a whole bunch more. But when we have it in that final form, we can see where the zeros are. Those are all the locations where the numerator polynomial goes to 0. And those are all at distinct locations, z1 through zm. The poles are all at 0, because what makes the denominator polynomial go to 0 is z is equal to 0. So we're going to be moving towards this idea that this is n of z, or d of z, or sometimes we'll just use different letters. We'll use b of z for the numerator polynomial and a of z for the denominator polynomial. But in the case of this example so far, the denominator polynomial is just z to the m, which has all of its roots at z is equal to 0. So take an example on that. If we start off with this second order impulse response, z transform it, put it in positive powers of z, we can now look at in this form right here, and we can say, what are the roots? Well, the roots are what makes that numerator polynomial go to 0, and one root is z is equal to 1/2, or minus 1/2, and then z is equal to plus 1/3 is the other root. And then there's two poles in the system due to that z squared in the denominator. Oops. And I'll just introduce this because this is so easy to follow. I think it doesn't hurt to start early. So something that we start doing a few more pages from now, but I'll just go ahead and do it with this example. Put up the z-plane. So it's looking at the complex plane where z resides when we've done the transform. And we're going to find it useful later to actually plot the locations of the poles and the zeros. So in this case, I said there were we can see that there's a 0 where? Minus 1/2. So we use little zeros for the zeros. So there's a 0 sitting there at minus 1/2. And then there's a 0 at 1/3. So there's another one sitting in here. And then there's 2 poles in here, right? That's where the denominator roots go to 0, where the denominator goes to 0. And so there's actually 2 poles sitting in here. And usually you just put a number next to it if they're repeated. Now right now, this you're probably saying that's a cute picture. What good is that? Well, we're going to spend more time developing what that means too. It's called a pole zero plot, and MATLAB has a function called z-plane, which we can put in the b vector and an a vector. And right now the a vector just equals 1, but if we were to put our b vector in there, we would get exactly this plot that I sketched out. So MATLAB has a handy function for doing that. Probably not too surprising though. If it's important, MATLAB has it built in usually. Of course, once we have the impulse response, we can go to the difference equation, or we can come back from the difference equation from the z-plane if we want to. But in this case, this is our difference equation. Well, excuse me, we could come at this from a different angle. My brain went off in a different direction. This is just another example. Basically, I went from the previous example and jumped into a related example. We had delta of n plus 1/6 delta of n minus 1 minus 1/6 delta of n minus 2. So the point in this example was to say, okay, now I have, this is my difference equation. What is h of z? So how would you find h of z for this system? There's a couple different approaches. One we can't really do formally without me cheating. I mean, I can do it, but you can't do it because you haven't been instructed that it's legal to do this yet. I'm saying that facetiously because if I can do it, you can do it. You just might not have the same understanding, but you're going to get that understanding. Formally, though, how would we do this? How would we find h of z? From what we've just gone, what we know so far, what do we have to do to be formal about it? You have to z-transform the impulse response, right? That's what we know how to do right now. So what's the impulse response for this system? It's replacing x by delta of n, right? So if we do that, then we will get h of n equals 6 delta of n plus delta of n minus 1 minus delta of n minus 2. And then we can take that to be h of z, and that will be 6 plus z to the minus 1 minus z to the minus 2. And then if I want to put that in terms of positive powers of z, I would have 6 z squared plus z minus 1 over z squared. And then what I could do next is I could factor 6 out in front, and I'd have 1/6 z squared plus 1/6 z, excuse me, did that wrong, z squared plus 1/6 z minus 1/6 over z squared. And this is the exact same polynomial that we had up above, except there's a gain scale factor of 6 in there. Notice this is what we had up here. It's just that there's not a 6 included down here. So the zeros are the same locations as before, it's just that there's a different scale factor on here. So this is also pointing out something that when you just look at a system function and just look at its zeros and poles, you can't really depict the gain of the system. And we'll explore that more probably in an example or a homework problem at some point. But the roots in the numerator and denominator are identical. I just sort of threw that in just to get you thinking about things that can happen. Okay, formally now we're going to go look at some other properties so we can make more headway towards the convolution sum, or the convolution theorem for Z transforms. So one of which is the linearity property, which we've already been using. You use the linearity property in problem number 5 of the homework. It's just stating the obvious. If you have the properties of sums, means that the linearity property applies. Because if we go to Z transform, a linear combination of two inputs, A times x1 and B times x2, the property of the sum operator means we can break that up into separate sums, and then we can pull the constants out in front, so then we can conclude that we could have just Z transformed x1 and x2 separately and then applied the scale factors A and B independently. So that's a property of the Z transform. The time delay property we looked at in a special case of a delta, but if we want to Z transform any signal that's been shifted by, say, one sample or n not samples, we get the corresponding result that's the Z transform of the unshifted signal times either Z to the minus 1 or Z to the minus n naught. So this is called the time delay property. And if I was putting boxes around things consistently, I probably would have had a box around this page in the notes with, if I really wanted to show favoritism or show it properly, I'd just show that case, because this is the most general case. A time delay by any number of samples, left or to the right, reflects itself out in the Z domain as a Z to the minus n naught times the Z transform of the unshifted signal x of Z. And the proof of it is just, again, looking at how x of Z would be some linear combination of constants, say alphas and powers of Z. And if I come along and multiply that Z transform by, say, Z to the minus 1, that puts an extra negative power of Z in front of every term. So now we start at minus 1, minus 2, up through minus n minus 1. And then if you inverse Z transform those term by term, you see that there's an extra delay in each of the terms. So that brings you back to concluding that that shifted the sequence in the special case of one sample, but generalizing it to n not samples also applies. So what's the significance of that in the homework problem that you had, just as an aside? Remember this in the homework problem? That was the very last problem number 6. What this says, we could apply linearity to this, and we could take the Z transform on this side, and that becomes Y of Z. and then take the z transform of that, and that becomes what? X of z. And what's the z transform of this last term? So somebody said because of the n minus 1, there's a z to the minus 1 that pops out, and then there's an x of z that's in there, right? And then the conclusion would be that this would be 1 minus z to the minus 1 times x of z. Okay? What was one of the roots that you found for y of z? Plus 1, right? And there it is, factored out. So one of the roots here, one of the zeros, let's call it z sub 1, is equal to plus 1. And then this guy over here would have some additional roots inside of it. It's pretty cool, I think, that it's just algebra. It's just nice, easy stuff to lay down on the page. There's no j's floating around necessarily, no e to the j's or anything like that. Okay, general z transform formula. I already hinted at this a few pages ago, that actually it extends to doubly infinite sequences, and that's in particular something that we need in Chapter 8. So now we were just talking about is actually what I just did in that little example from the homework is the z transform as an operator. I was kind of jumping ahead a little bit because for me it's just so tempting to just start going into it. So I guess what I have to ask you is if something's not making any sense, stop me, because this stuff flows out pretty logically, but I've been doing it for a long time, and I have a very hard time remembering what might have been a stumbling block for me, just because this seems rather logical. But logic, even for engineers, sometimes defies thinking, right? Would everybody agree that what seems logical maybe a few hours after you've absorbed it, you can't remember what confusion might have been in your brain when you first saw something? So the unit delay is when we take a sequence and delay it by 1. Based on what we were just talking about with z transforming x of n minus 1 into z to the minus 1 times x of z, that was the theme at the top of the previous page, that for one thing justifies this notation of putting a z to the minus 1 inside of a block. It's telling us that corresponds to a unit delay. Unit delay makes sense physically, but once we know the z transform, now we know why we would have something like z to the minus 1 showing inside of a block, because we'd say, oh, that comes from the z transform, that when we delay by 1 sample, that's equivalent to the z to the minus 1 showing up in the z domain. To formalize that even more, the book says let's talk about it as an operator. Say that when we send a signal through a z to the minus 1 block, that's like putting some operator on the signal x of n, and that's this equation right here that just simply shows the operator giving that 1 sample delay. I'm okay with that. I'm not a super big fan of it. It's something that they have in the book. I think you can get by just thinking of this result all by itself and then just visualizing the block diagram. So going back to what was in the homework and what I scribbled down 2 pages ago, if we had a difference equation or a filter of this sort, and maybe some of you observed this when you were working the homework problem number 6, because this actually works that same thing out. Just visualize an expanded version of that operator as saying that the effective operator to get x of n is just a unity operator, so there's like a 1 in here. And then the effective operator to represent the x of n minus 1 is the I guess I put that in the wrong place. There's a 1 sitting out in front here, and then there's the z to the minus 1 sitting out in front of the x of n minus 1 after the z transform. So that's their notion of, another notion of viewing it as an operator. Again, it's not my favorite, but I'm just passing through. If we were to just apply that idea, the operator idea, and just sort of not have to write down the steps, but just visualize what it means, we could now work this block diagram problem in the z domain if we wanted to. So we could say x of n enters this 2-tap FIR filter, so the signal x of n goes through the delay block and comes out as x of n minus 1, but in the z domain, how does that come out of the block? Effectively, x of z goes in if we think of transforming x of n to x of z at the input, and then the delay block, because it's delaying the sample by 1, means that what comes out of there in the z domain is z to the minus 1 times x of z. And if you're thinking about how the operator works, it's just simply x of z times what's inside that block produces the output. And then, of course, as we flow through the two multipliers, this path over here just has b0 times x of z on it. And this path down over here just has b1 times z to the minus 1 x of z. So that gives us those two terms to contribute to the output y of z. Because if we transform this, we get y of z. Then, of course, we can take things back to the time domain by just inverse transforming down to here. Again, operationally, y of z goes back to y of n, and then term by term, the y of z goes back to x of n, and then term by term, we group these two things together and say that goes back to, through the inverse transform idea, to x of n minus 1, because of the notion that a z to the minus 1 out in front of an x of z implies that what we really had was x of n minus 1 out in the sequence domain. Is this all making sense? You don't have to be necessarily a super engineer to think this way, but the average person on the street would probably say, they'd probably walk away from you a long time ago because they wouldn't even know, why do you even care about this stuff? You know, modeling signals like this. But you do have to be a little bit abstracted in how we think of this. Just think of y of z and y of n as being, you know, two sides or two different worlds you can be in. The time domain, like I said, is the real world where signals really process. They make a difference. We hear them. We might see them displayed. The z domain is like going into an alternate mathematical representation that's abstracted, but it's useful for getting certain types of representations or understandings or getting a certain amount of work done. So now we're ready to formalize the convolution theorem. For the special case of a delay system, we know that when we convolve x with a delta, that always replicates the x with whatever the delta was shifted by, so that gives us the x of n minus 1. And we know that the z transform associated with that delta of n minus 1 is z to the minus 1. And we know from talking about the delay operator that that gives us z to the minus 1 times x of z. So from this, we observe sort of informally that it must be that y of z is h of z times x of z. This is kind of a backhanded, not very detailed proof of that idea. The formalization of that is in the proof, though. In other words, this is what is known as the convolution theorem. For z transforms. Because it's starting off over here by saying that y of n is x of n convolved with h of n. So to actually prove that out, the book's approach and a plenty handy approach to prove that out is to just replace the x of n convolved with h of n with the convolution sum, because that's what we know right now when we believe in that, because we've been studying that for a while. So as soon as you take the convolution sum, what are our options? If we want to show what y of z is, what do we have to do? We formally have to come in and take the z transform on that side and take the z transform on that side. We're keeping things in balance. So on the left-hand side, we get y of z. And on the right-hand side, as we take the z transform, what's going on? Well, the book has kind of pulled a fast one. They said the z transform operator is formally looking to multiply what's inside by z to the minus n, right? In other words, you have to think, and this is kind of missing from my notes, that we have to think that we have a sum outside of this we have that going on. So as we delve into this further, we see that the z transform operator was with respect to the index on n. So what the book does at this point is it, and get the colors to shift. It takes that sum with respect to n and moves it inside of the sum on k, and in so doing it's saying, oh, I'm just going to hover around that thing right there because that's a function of n, and apply the z to the minus n to that, and by our operator idea, that should just be the z transform on x of n minus k, which we know is going to be z to the minus k times x of z. So that's why that gets plugged in over here. Is that okay? So we're interchanging the orders of the sums. We're going to do the one on n on the inside and the one on the k on the outside. And from a pure mathematician standpoint, that has to be justified. From an engineering standpoint, we're just boldly doing it. We're assuming that the signals of interest to us still converge, or at least the sums exist. So we go inside there, we see that x of n minus k, and from what we've been seeing, when we z transform a signal x of n minus k, that becomes z to the minus k times x of z. So we're doing it operationally. We're not looking for the z transform on x per se, because we don't know what x is. We're just getting our result in terms of x of z. So the slick thing about doing that is, as soon as we've done that, then this z to the minus k can now be slipped inside of the parentheses here, and that becomes a z transform onto itself. That becomes a z transform x of z, or h of z, and then x of z is sitting next to it. So then we've got the proof done. I don't know if you followed all of that, because it almost looks like a magic trick. I mean, a sleight of hand deal, where all of a sudden it pops out. But formally, we took the z transform of the entire thing, and then interchanged the orders of the sums, and then the x of n minus k became the z to the minus k x of z through the z transform, and then that z to the minus k went over and associated itself with the h of k, and then that was identified as a z transform on h of k, and then we had it. So from a proof standpoint, it's about being bold, just saying, I could stare at this and nothing's going to happen by staring at it. I have to take action. So the action in this case was to interchange the order of the sums, and then something some action could take place. We could get something to move, basically, by taking that action. So from here on in, this is now legal to accept the Z-transform convolution theorem. So this allows us to skirt around convolution if we choose to work in the Z domain. So an example that I put up is two finite duration sequences. From what we were doing a few chapters back, remember with the table method we could have said, okay, I've got a 2, a minus 3. I'll do that right. We have a 2, we have a 0. We have a minus 3 spike, and then we have a 4 spike in here. And then down here, we have a 1, a 2, and a 1. A couple chapters ago, we would have gone and said to convolve these two sequences, we'll set up a table. Remember? To convolve two sequences. So now we can use the power of the Z-transform to skirt around taking and setting up the convolution table. So now now the approach is going to be go for x of z and h of z, and then multiply to get y of z, and then inverse transform back to get y of n. That'll be the procedure. So working in the Z domain means we have to do a little bit more algebra manipulation, but we don't have to actually do the convolution. So we switch over to the Z domain with both sequences, h and x. Then we multiply them together, which means we have to do some polynomial multiplication. After we do that multiplication, we observe we get up to a 5th degree polynomial. We have to collect like terms. And when we collect up the like terms, which is what I've already done here, we can see that the inverse Z transform falls out naturally. So we've avoided formally doing the convolution table, but guess what? We've actually done the convolution by just multiplying the two polynomials together. If you remember, the coefficient set that goes with polynomial multiplication is like convolving the coefficients of the polynomials. Remember you talked about that, and that seemed like kind of an abstract, oh, by the way, this is true, but it doesn't seem relevant to our work right now. In the case of what we're doing at this moment, though, it's exactly that. When we multiplied those two polynomials together to get the new coefficients, we were effectively carrying out the convolution of the coefficient sets when we did the multiplication and collected like terms. And once we got the like terms put together, then we've got our sequence back. But still, I'll grant you, in my opinion, this is more methodical. There's less likely to be an error than setting up the table and having to fill it all in. This is something we're more accustomed to, just multiplying polynomials out. So that's the output sequence. Does the output sequence have the right behavior from what we learned? And it looks like it starts at 0 and ends at 5. Is that correct from what we started with? We started with 0 and 0, and we ended with 3 and 2. So, yeah, that's right, because 0 plus 0 is 0, and 2 plus 3 is 5. I just didn't fill in the values here, but you could go ahead and fill them all in. Any questions? Maybe for a Monday morning it's not waking you up, I don't know. Remember, I'm under the influence of a bunch of Advil right now, so I'm kind of doped up feeling myself, but I don't know what your excuse would be if you're if it's not getting you somewhat excited. What's that?
Oh,
Nothing? Okay. Well, here's the alternative. Suppose we didn't have the z-domain now. We wanted to just do the convolution directly. I'm not going to work out all the details, but what would we have to do? We could set up the table method, or like we were talking about last week or the week before, I can convolve delta functions together, right? So if I had to convolve it directly, what I'd be talking about doing is I'd be talking about convolving this times this, which means I'd have to do 2 delta of n times delta of n, which is what? That's a delta of n, right? Remember, we can think that x of n convolved with the delta of n minus n naught gives us x of n minus n naught. And if we just let x of n be a delta of n, then, and n naught is 0, then we just have delta of n convolved with delta of n is delta of n. So that would take care of itself. Suppose we wanted to convolve this term with that term. What would that turn out to be? That should be 4 times delta of n minus 5, right? It's a little bit goofy, but you can think of the first delta there as being like the x of n, and the second one being the delta of n minus n naught, so it just shifts the first sequence over by 2 more samples. So those would be the steps that you'd have to go through to do it directly. Which, again, I think a more methodical approach is to go about getting y of z and then inverse transforming term by term. It's just a little bit more structured and maybe less likely to make errors. So the formal box statement of the z transform convolution theorem is this guy right here. We're going to be using it the rest of the semester. It applies now forever and forever, and any problems you bump into, you know it's true. The only time it will be off limits is if on the final exam I say you must do the problem using a time domain convolution, or maybe it would be a problem where you're going to compare, the z-transform approach to a brute force convolution, and I'm just asking you to verify something. But unless the problem specifically says you can't use the convolution theorem, you should always contemplate using it, because the chances are it's going to make life easier, or at least make it less error prone. So now that we have the convolution theorem, now we can go ahead and jump right into the cascading result. We've seen the cascading result in the time domain. We've seen it in the frequency domain. What does it look like in the z domain? Same idea. We put in x of n, and that's equivalent to the x of z. So it produces a w of z. But w of z, as it comes through the system from the convolution theorem, is just going to be h1 of z, which is the z transform of the impulse response of the first system, times x of z. And then we carry the w of z through to y of z, and that means we just go through w of z multiplies times h2 of z for the second system. So now if we want to relate y of z to x of z, we just make the substitutions, and we have, if we just substitute in this whole quantity in place of w of z, we have exactly y of z is h1 of z times h2 of z, and then times the input x of z. So cascading just means that we multiply the z transform of each of the subsystems together. Seems pretty simple, right? Cleaner than in the frequency domain. Remember, the frequency domain result was h1 e to the j omega hat times h2 e to the j omega hat. This is an example I had you look at when you were working problem number 4 or problem number 6 in the homework. Just an example of using MATLAB's roots function. Here's a third-degree polynomial for some h of z, and just use the roots function with the coefficients loaded in to the roots function itself, and it returns a vector p whose elements are the roots of the polynomial. So those are the 3 roots of the third-degree polynomial. And the statement down below here was just, this is the check, is all this is. Just to check to see that if I was to multiply all the polynomials together, the first degree polynomials, I would get back to, or I could get back to what I started with, or at least I could get back to partially of what I started with. I'll explain that in a second, but the roots function, simple enough, right? If it's a third degree polynomial and the coefficients of the polynomial are real, you've learned somewhere along the lines in your math life that what are the roots of the polynomial going to be like. If you have real coefficients on an nth degree polynomial, you have n roots, and the roots are restricted to being real roots or complex conjugate root pairs. Remember that from something in algebra along the way? And in this case, with this third degree polynomial, we ended up with 1 real root, and then we ended up with 1 complex conjugate pair. So another way of looking at this result that I kind of got hung up on just doing as an extra little demo in here was, formally, if I wanted to recreate the entire polynomial h of z, I could say that it's like I have a cascade here of h1 of z is 1 minus a minus 3.62 whatever z to the minus 1, and then in here I have an h2 of z, which is 1 minus 0.3137 plus j 0.4211 z to the minus 1, and then I'd have a third system, h3 of z, so I have 3 first-order systems now, and if I put them in cascade, I should be able to get h1 of, or h of z should be the product of all of those, right? Or I could take h2 and h3 and multiply them together, which is what I'm doing here. And the reason why I'd multiply them together is so that I could get real coefficients in that subsystem. So h4 of z has these coefficients. Just has 1 minus 0.6274 and 0.2757. So it has real coefficients, and h1 has the real coefficient. So I could build the system back up again by multiplying, and here I called it h1 and h2, but by first degree and second degree systems. So you could build it up as a cascade of a first and a second, and if you multiply it all out, which I did with a triple triple convolution, get the original coefficients, 1, 3, minus 2, and 1. And putting x's through those zeros because MATLAB's not perfect. It's getting a tiny, tiny imaginary part, but I know better. I know that it's got to have real coefficients when I get done. So I was just sort of extrapolating beyond what was in the original problem statement, just saying you could break it out into a cascade if you wanted to. Does that bring up any questions? I probably got you confused by just going around in circles and doing different things. I'm just letting you know that there's all kinds of things you could do. But also just showing you some of the tricks you can pull too. Before we go look at this next topic, I want to go jump over to something else that is going to get talked about eventually, but because I can't remember where and because it just seems like I need to do it, I just want to show something, or at least it's something that I know is going to be coming up in my office sometime with somebody coming in for a question. Now I know what it is. I've got an appointment right at 3 o'clock. We already know what h of z is for the first order, or for the FIR filter, but let's get at it another way. Let's just start with the difference equation directly rather than the impulse response. So we'd like to find h of z. So we could go after the z transform of h of n, or another approach, one that I'm going to just demonstrate to you right now, is we could also just z transform both sides of the difference equation. So we have y of z on the left, and what do we have on the right-hand side? We get to use several properties. We get to use linearity and the time delay property that we've already investigated. So if I do that, linearity says that the coefficients just hang out. They don't change to anything different when we come through. And then what is the z transform of each of those terms, x of n minus k, in an operational sense? It's just the z to the minus k times x of z. So how is this going to help us find h of z? Well, we have the convolution theorem, which says y of z, which is the output of the system, is h of z, the system function, times x of z. So all I have to do now is just do some rearranging on this equation, leave y of z by itself, pull the x of z that's hanging out on the other side underneath. So I'm going to move this over, effectively down underneath on that side. And as soon as I do that, I know that as soon as I've pulled this effectively underneath here, what I'm left with is h of z, right? H of z is y of z over x of z. And this is probably a more powerful way of even thinking of the system function. Later on in the next semester's course and thereafter, sometimes people just don't call it the system function. They just get in the habit of calling it the transfer function. And the transfer function notation comes about because it's the ratio of the output over the input. It's telling us what the ratio is from output to input, or input to output, excuse me. So it's how the input gets transformed to the output through the h of z. So we can rearrange the algebra and say y of z over x of z, which is just h of z. And then what we're left with on this side is just simply the bk z to the minus k as k runs from 0 up to m. And for the FIR filter, we might just say, well, it's b0 plus b1 z to the minus 1 all the way out to b sub m z to the minus m. See how easy it is to just sort of spin the algebra around? So that doesn't require or didn't require going through the impulse response. We could just work straight from the difference equation and do some rearranging. We're going to make use of that in the next chapter as well. So I wanted to at least scratch through that once before I started doing it in my office on a more regular basis. Hopefully this will cut down on the number of times I might have to answer that question. Any tricks you can learn and remember will just make things easier in the future. So now we're to the point where we can get back to something that you were doing in the lab last week. Cascade 2 systems. Remember, you were doing deconvolution in the lab. The second filter was supposed to undo what the first filter did. So we wanted to have the overall system response be 1. So we wanted to have the cascade response be 1. So if we have h1 of z, h2 of z equaling 1, that says that h2 of z should equal to 1 over h of z. Sounds easy enough. What does that mean? Well, let's take an example. Exactly what you had in the lab, except the system order is changed. The first system is 1 minus a z to the minus 1, and what does that transform back to? That just says y of n is equal to x of n minus a x of n minus 1. This was the second system in the lab, right? If I'm remembering correctly. So the inverse filter is just 1 over that. So it's 1 over 1 minus a z to the minus 1. This happens to be what's called an IIR filter. We're going to deal with those types of filters in the next chapter, and we'll see how conveniently they are to work with and so on. But right now, just sticking with the idea of an FIR filter, we could do long division on that. So if we did long division, divided 1 minus a z to the minus 1 into that unity numerator a bunch of times, we could get out of it terms like 1 plus a z to the minus 1 plus a squared z to the minus 2, and so on. And if we did that long enough, eventually this becomes a smaller and smaller remainder. So much so that we could decide to forget it, or at least ignore it. So the approximation would be to keep all the terms from long division, just m of them, and just ignore that remainder. And that's exactly what went on in lab number 8. Remember, this was the first system in lab number 8, but it's the same idea. And what was the consequence of ignoring the remainder? What do you recall? And what that error was just a nice little ripple, right? It rippled around unity for the magnitude response, and the phase rippled around 0. If you were to take m up to a higher and higher number, it would get tinier and tinier. And I encourage some people to do that. I don't know if anybody tried it just for the fun of it. I mean, you don't have to be that crazy, but sometime you might want to take a look at it. That's kind of how you discover things sometimes too. You have a spare second or two and you say, let's just check this out and see what's going on. You might sometime in your life find yourself doing that. You might have an important discovery that your manager will be very happy that you took the time to do. I'm subtly saying, score points, get a raise, save the company some money. Maybe it's, and that's dreaming like that can be valuable, or at least educational. We'll come back and we'll look at this, the official inverse filter when we get to Chapter 8. It will be a first order IIR filter to build that H2 as shown here on the page. I think that's a pretty good point to stop in the notes, since I did bring in Mathematica with a little example or two in here. This is just a 3-tap FIR filter of which I can dial the coefficients up and down. So here I'm just sliding the center coefficient B1 and leaving B0 and B2 alone. You can see that we're putting in a variable frequency notch, just like we were looking at earlier. And now if we go through, I've got the phase there, if we go through and do the same thing in the Z-plane, just change that center coefficient. Notice here's where the zeros are, and there's 2 poles sitting right in there because there's a z squared in the denominator. If I slide this back and forth, notice that the notch was moving around on the unit circle, or moving around, the notch frequency was moving up and down the frequency axis, but now the zeros are just moving around on the unit circle when I do that. And there's going to be a nice relationship in the z-plane to the frequency response, namely the angle that the zero makes to the positive real axis is in one-to-one correspondence with the location of that zero. I put a little plot for the, let's see which problem, one of the 2 bonus problems on this last assignment. I put an extra little plot. No, I guess somewhere or another I did something in one of the solutions, either for the homework or for the quizzes. I'm not sure which. I think it was in the bonus problem. We had to find the frequency where the nulls occurred in the filter. I used the angle that the zeros made to find that in a little bit slicker fashion. Another thing you can see from this thing, which is kind of intriguing, this is a second-order polynomial, so it's basically the roots of a quadratic. You can see if you change the leading coefficient, the root goes flying off like that, but if I get bigger and bigger, now the roots are back on the real axes again. Or you can play other games in just factoring a quadratic. Let's just try to make it so they stay in view here. I guess that's not the right combination. I was playing with this before class, and I had kind of a nice setup on here. Okay, they're coming off from being complex, and now they're real. Remember how the discriminant in a quadratic equation goes from being square root of a negative number to positive? So there are 2 real roots, and now they're flying off in complex conjugate pairs. All that stuff is going to be part of the game plan now, to have that extra insight, and then the locations where the zeros might be sitting or residing. And MATLAB helps, of course. This is done in Mathematica using some tools that I wrote, but the same thing can be done in MATLAB.